Welcome back to 100 Days of Logic with Carneades.org. Today we are continuing with the final 10 days of logic, looking at predicate calculus. Today we're going to be looking at conditional and indirect proofs. Now, it's actually going to be pretty easy to do these because these are going to be very similar to the conditional and indirect proofs that we saw in normal propositional logic. If you don't know what I'm talking about, check those out in my series earlier in the 100 Days of Logic on conditional and indirect proofs. There is, however, going to be one important difference that we need to note. As I mentioned when we were talking about the rules of instantiation and generalization, I said there was going to be some extra caveats that we would add to universal generalization. Here's one of them right now. Universal generalization, going from things like y is an f to for all x, x is an f, cannot be used in the scope of a conditional or indirect proof if the instantiated variable y is free in the first line of the indirect or conditional sequence. That was a lot of words. What does that mean? Well, we should be able to understand most of what this means. The first line of the conditional or indirect proof is that first indentation, that thing that we're assuming, that we write either ACP assumed conditional proof or AIP assumed indirect proof next to. The instantiated variable is just going to be the variable in there, y in this case, is free. What does that mean? A variable being free? Well, we haven't learned that term yet, so let's take a look. You can have free variables and you can have bound variables in predicate calculus. A variable is free if it's not bound by a quantifier. Examples might be x is an f or y is an f. Some examples of bound variables would be there exists an x such that x is f, or for all y, y is an f. So if you have something like x is an f or y is an f in that first line of your conditional or indirect proof, you're not going to be able to use universal generalization on that specific variable derived from that line in some way. Why is this going to be invalid? Well, let's take a look at some examples. So, we remember, universal generalization may not be used in the scope of a conditional or indirect proof if the instantiated variable y is free in the first line of the indirect or conditional sequence. Let's take a look at the following proof. For all x, x is a p implies that for all x, x is a q. Therefore, for all x, x is a p implies x is a q. Don't try to do this on your own because it's actually invalid. It's not a valid argument. The conclusion does not follow from the premise. You can have a true premise and a false conclusion. The reason it's going to be invalid is it can only be derived by using the invalid version of universal generalization. Or probably some other ridiculous rule. But that's what we're focusing on here. What you would do if you were trying to incorrectly prove this would probably be to assume, with your assumed conditional proof, x is a p, and you draw your line going down. Then you would universally generalize premise 2 to for all x, x is a p. It's going to be invalid because, as we said, we can't use universal generalization when the variable is free. X is free in that first line, P2. It's free because we don't have any quantifiers around it. There's no for all or there exists. We're not allowed to use universal generalization. But let's continue just to get an understanding. We would then go ahead and do 1-3 modus ponens to get for all x, x is q, and conclude x is q from premise 4, universal instantiation. We could conclude from that premises 2 through 5, conditional proof, that x is a p implies that x is a q, and it would just take a universal generalization to get for all x, x is a p implies that x is a q. Now, I've told you this is invalid, and you may be able to see that it's invalid from the use of universal generalization incorrectly, but right now it's a lot of symbols, so it may not quite make sense that it's invalid. So I'll translate it into something a little more concrete. Let's take premise 1 and say that it is, if everything is a paper plane, then everything is a quail. This is actually going to be a true statement because it has a false antecedent. The first part of the statement, that everything is a paper plane, is not true. So the whole conditional is in fact going to be true. Our conclusion is all paper planes are quail. This should clearly be false, because there are definitely paper planes that are not quail. In fact, these seem to be pretty exclusive categories. Because we have a true premise and a false conclusion, this is an invalid argument. One of the reasons it's invalid is because if you try to prove it, you're inevitably going to have to use universal generalization inside a conditional proof on a variable that was free in the first line of that proof, or some other invalid method. The point is, it's invalid, and this is something you can't use. This is also going to be a problem for indirect proof. We'll take a look at an example of that here. So, our argument is there exists an x such that x is s, or there exists an x such that x is r. For all x being s implies that x is r, therefore for all x is r. We're going to start off with an assumed indirect proof. That's just kind of the negation of the conclusion, but note that the variable x is free. There's no quantifier on the outside of it. We'll draw our line going down. Then we would do our invalid universal generalization, which is going to be for all x, it's not the case that x is an r. Once again, it's going to be invalid because we're taking that free variable in that first line of our indented sequence, and we are using universal generalization on it. Then we'll do change of quantifier to get it's not the case that there exists an x such that x is r. We'll do disjunctive syllogism from 1.5 to get there exists an x such that x is s. We'll get a is s. Premise 6, existential instantiation. We'll get it's not the case that a is r. Premise 4, universal instantiation. A is s implies that a is r. Premise 4, universal instantiation. It's important to note that we did our existential instantiation first and then we did our universals. If we had done our existential second, we would have had to use a different constant in place of a. Then we will get Ra from premise 7, premise 9, modus ponens. And finally, we will get Ra and not Ra from premise 8, premise 10, conjunction. This is a contradiction, so we can deny our original assumption. That gives us just x is an r, premise 3 through 11, indirect proof. We can then, of course, universally generalize to get for all x is an r. Once again, it may not be clear right now that this is an invalid argument. So let's assign some actual ideas or some concrete objects and predicates to these premises and this conclusion and see why it's invalid. Premise 1. Either a square exists or a rectangle exists. We're substituting square for, or is a square for s, and we're substituting rectangular is a rectangle for r. Premise 2. All squares are rectangles. It's going to be a true statement. Both of these, in fact, are true statements because at least one square or rectangle exists, and all squares are going to be rectangles. However, our conclusion is actually that everything is a rectangle. For all x is a rectangle. That's clearly going to be false. There seem to be things that are triangles, circles, or tuna fish sandwiches. So those things are not rectangles, so our conclusion is going to be false. We have true premises and a false conclusion, so we had an invalid step somewhere in our argument. Of course, the invalid step was in premise 4, where we incorrectly used universal generalization. Hopefully that makes sense. There's going to be one more caveat we're going to add on to universal generalization in a future video, but for now, put that into your brain, practice with some conditional and indirect proofs, and that was conditional and indirect proof. Next up is proving invalidity. We're going to look at counterexamples, which we actually looked at in this video, and finite universes. Then we'll look at relations and overlapping quantifiers, identity, modal logic, and some final logic problems and the answers. Watch a new video every single day for 100 days here at Carneades.org, and stay skeptical, everybody.